Hello and welcome to the 8th video in our series on labor search frictions. In this video, we finish with the setup of the DMP model by discussing how search and matching works inside the model. So the first thing here is we want to get two things. We want to get the total number of matches, which is going to be equal to the total number of employed consumers, and the probability of finding a job and filling a vacancy, of course. Okay, so those are the things, these probabilities and the total number of matches. We're going to be using a matching function to determine the number of matches. This matching function is a mathematical way of embedding into the model the fact that there are search frictions that prevent all matches from occurring. So what is this matching function? We're going to have that the total number of matches, uppercase M, it's going to be equal to E, the matching efficiency, more on that in a moment, times a function that's going to depend on Q, the total number of people in the labor force. Remember, these are the people searching for a job. And A, the total number of vacancies. So job openings, job searchers. We think of this the same way we think of a production function. If there are more searchers and more vacancies, you can generate more matches. E, the matching efficiency, is going to be determining how you can transform Q and A into more M, how you can transform this search into more matches. Okay? The important fact here is we do need that the total number of matches is less than, and there should be an E here, I apologize for that. The total number of matches has to be less than the minimum of Q and A. You clearly cannot fill more vacancies that are posted and cannot employ more people that are searching for a job. And so in this case, we want this inequality to hold. If the inequality holds strictly, there are search frictions because you generated less matches than the maximum number of matches that you could have generated. If you think about it, this minimum between Q and A, it's the maximum number of matches that can be generated. An example can be very forthcoming with numbers. If you think that there are 10 people searching for a job and 20 vacancies, then you can have at the most 10 matches. That's what this inequality is saying. Now, how many, remember, there is an E here, so this is the total number of matches. I just forgot to write it. Now, what this is saying is, depending on E, for example, if E is higher, that increases the number of matches you can get for any level of Q and A, for any number of searches. That's the matching efficiency. Now, as I was saying, M is just like a production function and has a lot of the same properties. The most important one for us right now is that M has constant returns to scale. If you double the number of searches and the number of vacancies, you're going to also double the number of matches. That's going to be important because it's going to allow us to manipulate this function in a very important way to get at the probabilities we're going to define on the next slide. There are other properties, positive marginal products. That means if there are more searches or there are more vacancies, then you're going to have more matches. The more of them you have, then the better. But there are also diminishing marginal products. And so, yes, you can add more people searching, you can add more vacancies, and that's going to get you more matches, but ever less. Okay? So, very similar to how you think about a production function. Now, how do we go from this definition of the number of matches to the probabilities? Well, it's going to be rather simple, but it does require some care. So the first thing is the probability of finding a job. So PC is the probability of finding a job for a consumer. It's very easy to define it as the total number of matches. This is the total number of people who find a job relative to Q, the total number of people who were looking for a job. Then we can replace M for its definition as the efficiency times the matching function. But because the matching function has constant returns to scale, then multiplying the matching function by 1 over Q is the same thing as multiplying each of the arguments of the function by 1 over Q. Remember that when a function has constant returns to scale, it is the same thing to multiply the function by a constant than to multiply each of the arguments by that same constant. And so what we're doing here by dividing by q is the same thing to divide m by q than to divide each of the arguments by q. That's why here we have a 1 and here we have an a over q. And a over q, it's an important fraction for us. A over q, that we're going to be denoting j, more on that in a moment, it's what we're going to call the labor market tightness. And it's going to be a critical argument for us when solving this model. So more on that in a moment. But for now, here is again what's happening. The probability that you find a job if you are searching is how many people found a job relative to how many people were searching. But those people who found a job, we know that's equal to the matching function. Now, because we're multiplying the function by 1 over q, or dividing the matching function by q, and the matching function has constant returns to scale, dividing by q the whole function is the same as dividing each of the arguments by q. That's what the constant returns to scale allows us to do. And so we can express this in terms of a over q, this ratio, which is going to be determined and defined here by j. Now, what happens for vacancies? It's pretty much the same story. The probability that a vacancy gets filled, it's the total number of vacancies that got filled relative to the total number of vacancies that there were. And now the same way as before, because we're dividing the matching function by a, and the matching function has constant returns to scale, that is the same thing as dividing each of the arguments by a. And so we can express it again in terms of j, the market tightness. So the final thing we need to see is what is this market tightness? Well, to start, it's just the ratio of how many vacancies there are relative to searchers. If you see, this is kind of similar to that beverage curve you were seeing before. How many vacancies there are relative to searchers is going to give you a sense of how tight the market is. Because if there are more vacancies relative to the number of searchers, the market is tight in the sense that it is easy for consumers to find a job and harder for firms to fill a vacancy. You can see this sentence in math here above. If j is higher, we know that m is increasing in j. If j is higher, that's going to increase the probability that you find a job if you are a worker searching for a job. But if j is higher, that's going to decrease this argument. And so it's going to decrease the probability that an individual vacancy is filled. And that should make sense. If there are more vacancies relative to the number of searchers, then that's going to make filling each of those vacancies harder, but it's going to make it very easy for any of those searchers to find a job. And so generally, when we're in a boom, when we're in an expansion, and a lot of firms want to hire, but people already have jobs, for example, we say that the market is tight. That is good for workers who want to find a job that's relatively easy to do. And it makes it hard for firms to hire. With that, we've now described the whole model. And in the next video, we're going to talk about how to find the equilibrium of the model, how to solve for all the variables. The key is going to be to find the value of j. Because as we will see in the next video, once you find j, you know the probabilities. And with the probabilities, you can solve for the rest of the model. Okay.